Morning everyone, my name is Pranay. I'm from CSC AML Section C. Today my topic of object-oriented programming, my report is sliding puzzle solver. Sliding puzzle solver. The sliding puzzle solver, particularly the 3 by 3 version of puzzle that is known as 8 puzzle, is a mathematically rich and computationally challenging problem used in various fields of research including artificial intelligence, robotics, optimization theory, and cognitive science. The puzzle consists of 8 numbered tiles and one empty space arranged in a 3:3 or 3 by 3 grid. By sliding the tiles into empty spaces, the player attempts to transform an initial arrangement into a predefined goal configuration. Is as simple as it seems, the slided puzzle belongs to a class of state space search problems that demonstrate important algorithmic principles. The puzzles can be represented as a graph where each possible arrangement is a state and each valid tile movement represents a transition to another state. Solving the puzzle involves finding a optimal path from the initial state to the goal state. Project objectives. I would like to speak about the project objectives. The main objectives of this project is to implement a fully functional solver using object-oriented programming concepts like designing classes to represent puzzle states, use encapsulation to maintain tile configuration, implement abstraction to hide algorithmic complexity, allow future extension using inheritance to apply a search algorithm for optimal solution finding, compute cost functions and heuristic values, maintain open and closed lists for efficient searching, explore minimal number of moves for a solution. Next, to represent puzzle as a state space model, each configuration is state, tile movements, transition between states, goal configuration, state that terminates the search. To use heuristic functions for intelligent searching, Manhattan distance heuristic, misplaced tile heuristic, and to demonstrate computational program solving skills, use priority queue for node expansion, maintain efficient hashing to avoid repeated states to produce structure and readable engineering level Java code. Next, system architecture. Our system puzzle solver follows a modular architecture consisting of puzzle state class. So the puzzle state class, it represents the tile arrangement, position of blank tile, and parent state for path reconstruction, the cost of movement G, heuristic value H, and the responsibilities. The responsibilities of this class is generate successors, compute heuristic, check a goal state, print state. A star solver class. A star solver class implements open list, priority queue, closed list, has set, a evaluation function fn is equal to gn plus hn. The responsibility of A star solver classes expand states, choose optimal path, avoid repeated states, construct final solution path. Main class handles input of start and goal states. Next, calling solver, displaying output. Activity flow, user set start and goal configuration. Puzzle state is created. A star solver begins with search and successor states are generated. Priority queue ensures optimal selection and goal found solution printed. Extended algorithm description. I would like to extend algorithm description. A search algorithm overview. Research uses the first main functions Gn, cost from start to current node, Hn, estimated cost to reach goal, and Fn is equal to Gn plus Hn, evaluation function. A always expands the node with lowest Fn, ensuring intelligent exploration. Algorithm steps. I would like to go on algorithm on a step by step. Okay, first step, initialize. First, start taking into open list, insert into open list, compute heuristic value hn for start. Now set gn is equal to 0, iterate. Let's start taking iterations. While open is not empty, pick node with lowest fn. If node is gold, terminate. Generate successor states. For each successor, compute GHF values. If not visited, add to open. Move to current node to closed list. Build solution path. When goal is found, trace parent references back to start, reverse list to show step-by-step moves, Advantages of using OOP for this project: flexibility, modularity, extensibility, and real world alignment. And I would like to explain all this. Okay. Applications of sliding puzzle solvers. Sliding puzzle solvers are not just toys, they apply to robotics, path planning and navigation systems, and logistics, optical arrangement of containers or items, artificial intelligence research, state space exploration and heuristic search, cognitive science, modeling human problem solving process, game development, building puzzle games and interactive systems. Next, complexity analysis. The sliding puzzle solver involves the A search algorithm whose performance depends heavily on the choice of heuristic. Time complexity. The worst case of time complexity for the puzzle is O into B power D, where B is branching factor, that is 2 to 4, and depth of the solution typically 10 to 30 moves. For poorly chosen heuristics, the search space grows exponentially and it becomes too hectic and too hefty at times. With the Manhattan distance heuristic, time complexity reduces significantly to fewer unnecessary states are also explored. Space complexity, it requires storing open list, closed list, all visited states plus transitions. Hence, it will be also an exponential case. And heuristic impact, Manhattan distance ensures optimally and strong pruning, whereas misplaced tiles heuristic is weaker and results in longer search trees. Stronger heuristic, lesser times, but higher computational overhead per node. OOP principles justification encapsulation. The puzzle state hides the internal details and the solver interacts through methods like generate successors or compute heuristic without knowing internal details. Inheritance, future extensions like BFS solver, breadth first search algorithm solver, depth first search solver, DFS, IDA solver can simply extend a base solver class. Polymorphism, different heuristics can be implemented by overriding a calculate heuristic method. Solvers can share an interface and behave differently at runtime. Abstraction, an algorithm hides eternal complexity behind high-level operations. Users only need to provide start and goal states. Testing and validation. One is unit testing. Test tile movement functions, validate successor generation in all directions, check Manhattan distance values for sample states. Integration testing, test connectivity between puzzle state and A star solver state, ensure correct FN value calculation and priority queue behavior. Validation against known solutions, use classical puzzle examples, easy 5 to 10 moves, medium 15 to 20 moves, hard 25 plus moves, ensure solver gives optimal move count. Challenges faced during development: one is state explosion, large number of configurations are possible. It requires careful planning, pruning, and using closed lists. Designing efficient heuristics, Manhattan distance computation must be optimized to avoid slowing down the solver, ensuring goal reachability. Only half of puzzle configurations are solvable. Must check puzzle clarity before solving. Path reconstruction, maintaining parent references without excessive memory usage. And project limitations: memory usage. It consumes significant memory with large puzzles. Execution time: hard puzzles may still take long time due to exponential growth. Limited heuristic, current model uses only one primary heuristic. Combining heuristics could be improved optimally. Okay. Future scope: support for large puzzle sizes like extend to 15 puzzle or 24 puzzle. Graphical use interface GUI using Java FX or Swing. We can create an interactive puzzle play. Implementation of additional algorithms like IDA, we can be reduce memory and we can use genetic algorithms and reinforcement learning agents. Integration with robotic simulation, use puzzle logic to imitate or mimic the robot. Mobile application version, Android based sliding puzzle can be interesting with internet solver. Engineering ethics and professional practice, using transparency and clarity in the algorithm, avoiding plagiarism by writing original code and documentation, testing thoroughly to avoid malfunction, respecting computational resources and creating efficient software. Next, real-time analysis of sliding puzzles. Warehouse create movement similarity to re-engineering crates where only one specific space is applicable or available. Parking lot management, moving cars to a free space requires strategic planning. Robot grid navigation, robots moving around obstacles use similar state transitions. I would like to conclude that the project which we have demonstrated, it It requires combination of mathematical modeling, algorithmic reasoning, and object-oriented designing through implementation of a such algorithm. The project highlights efficient problem-solving techniques and showcases the relevance of heuristics in reducing computational efforts. And with this, I would like to conclude my PPT, and I thank everyone for giving me this opportunity to explain my topic. And I hope it is clear. And thank you everyone again for giving me an opportunity. Thank you.